Good morning, Earth Science. Today we're going to be studying sun paths at the poles. Just as a reminder, we already saw the sun path as it appears to be when we're on the equator, on the Tropic of Cancer, and in New York State, which is at 43 degrees north latitude, so kind of halfway up from the equator to the poles. And today we're going to take a look at the sun path when we're at the poles. All right, so a couple of reminders. The motion that the Earth does around the sun is called a revolution. And while the tilt stays the same, the orientation of the tilt does not stay the same. I'm going to be using the actual sun today as my sun, so let's hope that this will work. Okay, so the Earth is tilted at 23.5 degrees. And when it's summer in the northern hemisphere, what we're going to have is that the tilt of the Earth is going to be completely facing the sun. And when that happens, even as the Earth rotates and you get that day-night motion, if you're in the Arctic Circle here, you're not going to see the sunset at all because you're completely facing towards the sun. So during 6 months of the year, if you're in this very special place, which there are only a couple places on Earth, a little bit of Greenland, a little bit of Canada up here, Norway, Finland, they're going to get 6 months of sun, 6 months of daylight without sunsets. It's kind of crazy. And then as the Earth travels around the sun, what we're going to get, eventually we'll get this, and that the South Pole is pointed towards the sun, and the North Pole here is not pointed towards the sun at all. So even as the Earth rotates, they're not going to see the sun at all. So for the other 6 months of the year, they're going to have complete darkness. And this is going to look kind of special on your sun path. Today I have this so I can show you what it would look like. I'm still going to label it east, south, west, north, and what it's going to look like is that the sun isn't ever going to set. It's never going to rise either. So what it just does, it does a circle. It does a circle. So the sun path for the North Pole and the South Pole is going to look just like a circle. And the sun path for December 21st, which is the winter solstice, what's it going to look like? It's going to look like it's not even on there because the sun never rises, never sets. So if you want to put it on there, you can put it as kind of a line that goes around the bottom, because it never rises from the ground. And there you go. So you only have two options. You got sun or no sun, and that's the case at the pole. So if you're drawing it on your worksheet, this is what it's going to look like. You're going to get one sun path like this for the summer solstice, June 21st. And then let me put this in another color, maybe in green. And then you're going to get another case like this that's never going to rise. And that's your December 21st, or your winter solstice. And between December and the equinox, the spring equinox, the sun is not going to rise. Between the spring equinox and the fall equinox, the sun is going to have this sun path right here, 6 months of sun. And this is the case for the North Pole, which happens to be 90 degrees latitude, 90 degrees north. All right, South Pole, exact same thing, except the summer solstice would be then December, and the summer solstice would be the summer solstice is December, and the winter solstice would be June. Just the months get flip-flopped because everything in the southern hemisphere has an opposite season. All right, we're going to also do a little bit about shadows today. So let me put this down. And all right, I've put Mr. Ducky inside of the glass dome, and we're going to do shadows. So remember I said in New York, the suns always are going to be in the southern part of the sky. So I drew some sun paths there. He's always going to see the sun in the southern part of the sky. What does that mean for Mr. Ducky's shadow? If the light is shining this way, his shadow is always going to be over here in the northern section. So what that's going to look like on your worksheet, you're going to have a spot where you have, you're going to use the website called suncalc.org, and you're going to put in Stanford, New York 12167, and you're going to see what the shadow orientation is and how long the shadow is. So, and there's a little simulation at the bottom that shows you exactly how great the shadow is. So, for example, let's put north, south, east, west. So when the sun rises over here, when we have a sun rising at the east, you should see a shadow that's pointing completely towards the west. And it's going to be a big shadow because the sun would be near the horizon then. As the sun starts to rise, and the sun is going to do something like this, and it comes to the southern part of the sky, the shadow is going to get shorter, and it's also going to point north. It's going to point north because the sun is going to be in the south. And then again, as the sun sets over here in the west, you're going to get another big shadow, but this time pointing east. So the shadow always does exactly opposite of what the sun is doing. In your simulation, you have to change a date so that you get the shadows for June 21st, December 21st, March 21st, and September 21st, all the solstices and equinoxes. And you're going to also look at the length of the shadow. The length is important because the longest shadows are going to be at sunrise and sunset, and you're going to compare them between these dates. So I also want you to write, for example, it could be 4.5 meters or 25 meters. I would also like you to label how big the shadow is. Or you can draw it to scale to the best of your ability. Your noon shadow should be very tiny, and your sunset and sunrise shadows should be greater. And if you have any questions, you can also email me. This packet, it was due at the end of today. If you think you're going to need a little bit more time, please email me. All right? I look forward to seeing you at Zoom.